那我们开始吧。天气越来越暖和，但是我们要学习。嗯，工程场理论。Okay, last time we talked about the Conformal block, how to compute. In fact, if you ask the Mathematica, I mean, it's easy to evaluate. So this is the code for the computing Conformal block, which you can find in the e-learning. So this one is the part which computes something like what we need to do is the what we need to compute is something like phi 1, phi 2, L minus lambda phi 3. Right? This kind of stuff we need to compute. This one you just bring this one into here and to bring this one into here and then just do some recursive relation to compute. And that you can program it. I mean, I'm not going to go into detail, but those are like some bilateral algebra and so on. And then cut metrics and so on. And then one can compute the, if I compute like this way, here's the result. Maybe I should make it bigger. Like this way. So this is the level 1 Conformal block when lambda is just lambda minus 1. And next is lambda minus 1 square or lambda minus 2 square that appear in here. That is the second block. So if you just factorize, so this one is the beautiful factorize it like this way. And then for the where is the, oh yeah, this part is the level 2 part, which you can compute. I mean, C0, not C0, D1, D2, D3, D4 are the conformal dimension of the external one. So, yeah, so those were conformal dimension of, and then C0 is the primary state, primary conformal dimension in the middle channel. So that's how you compute. And you can play around. I mean, it's fun to play around this one. So you can just, yeah. And this one, I mean, I don't know, I mean, okay, most likely you might have, you don't know that. I mean, this one, so-called, there's something called AGT relation. This conformal block is somehow related to the something called instanton. So the Yang-Mills instanton partition function. So anyway, so there is some relation between two-dimensional conformal field theory and the four-dimensional pseudo-sync Yang-Mills theory. And this is the correspondence can be found in the instant function. Anyway, so that's done. So that's you can see at the e-learning. So that's I just wanted to show. I mean, the procedure is I explained last time. So okay, fine. Okay, so today, okay, 今天我们学习正简化群 I don't know, renormalization. Group. So Is it the John? Is it? Huh? 정简. Oh, 重简. This is 重简. Like this way? Oh, thank you. Thank you very much. 重简. Okay. It's not. So what's the difference? When we become 重 and when we become 重? Can you explain to me? Anyway, 重简. Okay. Yes. So in quantum field theory, as I mentioned at the beginning of lecture, so the quantum field theory is not conformal usually. Usual quantum field theory, QFT. If you start with QFT, so it just it depends on scale. Usually depends on scale. On scale, you look at. And often, like a dimension is less than 4. Less than 4, dimension is the space-time dimension. So, space dimension less than 3. Or anyway, I'm a theoretical physicist, so I always include space-time dimension is D. Okay, then usually the ultraviolet. So at the ultraviolet, the high energy means high energy. High energy is the usually is the modifying QFT is the become asymptotically free. Well defined. Asymptotically free means that the coupling constant goes to 0 when energy goes to infinity, something like this. Energy becomes very big. But in the infrared is low energy. Okay, and then you have the path integral, as I mentioned, d by k and e to the middle. So some energy scale. So infrared becomes usually described by stronger coupled QFT, and then moreover often cannot describe by Lagrangian. So the infrared usually so in low energy you only have some effective field theory sometimes. If you're lucky, you have effective field theory, but you can usually the infrared quantum field theory cannot be described Lagrangian. And if you are lucky, so there's a so-called Wilson-Fisher fixed point or conformal fixed point. So another name is just the two are very same thing. Where coupling constant do not flow. Where G star is usually very big. And then at this point, the theory is described by, so in the theory described by Conformal, the theory. So people just often call IR CFT. So now for conformal field theory is that the locate a special point of the space of quantum field theory. So so that's we are going to learn today. So the goal is so in coming today and next time, so the goal is to learn renormalization. Group flow. So it's a 重建化群是不是群 so so it's not group. It's not group, so I need to explain what's the meaning or concept. It's not that, so that's what you need to learn. And also next we will learn so-called column semantic the function equation. So this is correlation function 关联函数满足这个 function. So next we are going to learn column semantic equation. Then we will learn Zamolodchikov. Zamolodchikov c-theorem. Okay, and then next we will learn so-called Lagrangian group. Minimum model of CFT correspondence or like a correspondence. So that's what we're going to learn. So this is also due to Zamolodchikov. This is also Zamolodchikov. So that's the 今天和下周的内容 ，OK， those are the plan of the coming lectures. The first of all, so what we need to do is that the renormalization group is not the important thing. Caution. So the important thing you need to keep in mind is that the first of all. It's not a group. Not a group. It's not a group. It's a really misleading name. So I will explain why. So it's not a. I mean, if you have a group, if you have an element G, if you have a G, there must be this G inverse. But this renormalization group is not it's not a irreversible process. So. I mean, there's no inverse. It doesn't exist there. Okay, G inverse. So it's not group. And moreover, often people misunderstood that this renormalization group is to get rid of infinity in quantum field theory. That's not true. It's not that. It's not a scheme to remove infinity in the computation. Okay. So those two cautions you need to keep in mind. I mean, often there is a misunderstanding that the renormalization group is just technique to remove infinity. That's not true. So these two cautions in mind, and I will explain why this is the case. So this is the notion of renormalization group flow is given by Ken Wilson. Ken Wilson, that's what we are going to learn from. And the explanation of this I'm going to give is this so-called Cardiff. So I'm going to be Cardiff's explanation. So let's consider life element, so lattice like this way. Like this way, the lattice, and then we can just integrate over. So you can do the whole so-called coarse grain. So you can just consider average of this big chunk. So that at each block you have a four lattice side, and you can average over. You can average over for each block. So which we call it the B1, B2, and B3, and so on. BI plus 1, BI plus 2, and so on. And then you just how to say average over 4 spin to give this spin number for each block. That's what we can do. So to do that, so it's called coarse graining n plus 1. You start with sigma 1, sigma 2 is some constant. So you just average all. You just sum them up at each lattice point. At each lattice point of spin, and then you just sum them up, and then just suitably normalize. So this is normalization constant. Normalization constant. Okay, so that's so this is an old spin variable to new spin variable, which I call it B sigma k. And then this one is the, so this is less information. So we already, so sigma 1 has more like a microscopic information than the sigma 2. So that's why it's called the coarse graining. This process is called coarse graining. Okay. And then we just sum them up with some weight, lattice weight, some operator. We call it T, sigma 2, sigma 1 is 0 when the K and R. Okay? So if this is the case, so sigma I inside of BK, but otherwise, like you just introduce this kind of operator. So if sigma 1 is inside of this, say when k equal to 1, so we only look at these pieces. So the T is 1 only for these 4 sides, the other side is 0. So that's what you. And then we impose this condition such that the TK2 sigma 1 I is equal to 1. So we impose all possible. If you just sum them up, or everything, you just sum them up, all the yellow block, so you should get equal to 1. That's the condition. So this is 2. So if you introduce this kind of like a weight of operator, so one can just consider the following thing. So the effective Hamiltonian. You just construct, so the Hamiltonian of the all Hamiltonian is something like that. Like this way, all Hamiltonian is like this way. From here, you just construct the effective Hamiltonian. So this is the old Hamiltonian, the effective Hamiltonian. So this is the effective. diverging over. So exponential sigma 2 is equal to something like that. This way is the old Hamiltonian. Okay, so like this. So you sum up all the configuration of sigma 1. Sigma 1 means this microscopic spin configuration with this weight. You just so this product. So this is just product of all blocks. So at each block you can define this T, and you just include all the blocks and multiply it with this operator, and then you have the microscopic Hamiltonian. So you just sum all possible spin configuration. You sum then to get the effective Hamiltonian. So that's the process we need. And because of this condition, if you do the following the Boltzmann, so this is of course I mean I'm suppressing one over kt, which is better in here, but I mean we just put the 1 here. So this is just Boltzmann weight. Okay, it's just Boltzmann weight. So therefore, if you sum over all possible configuration, the coarse grain spin exponential of minus h2 sigma k 2 g2 is sum over because of this condition, if you use this condition sigma i of 1 and the exponential of minus 1 h sigma 1 I 1 g1 like this. So I mean, if you sum up all possible this coarse grain spin, you get the 1. So therefore, this part is becoming just 1. So the product of y become 1. Okay. So therefore, the Boltzmann's average of Boltzmann weight of the coarse grain one is equal to microscopic order average of all the possible Boltzmann weight in the microscopic Hamiltonian. Okay. Microscopic, this is a bit more macroscopic coarse grain. So in this way, one can construct the microscopic Hamiltonian to coarse grain Hamiltonian. But you have to be careful about that this coupling constant is not necessarily equal to this coupling constant. Okay. So in this way, so G1 is equal to G2. So that you get a different coupling. This is coupling constant. Coupling constant in the theory. It can be many. It can be many coupling constants. Because there you can construct Hamiltonian with many interaction terms and so on. So these are the okay. In this way, one can just construct the so in this process, if you start with H1, you get the H2, and you get the H3, and H3 can be something like that this way. H3 is the further coarse grain. So from H2 to H3, you just have this kind of grain, this kind of coarse graining, and then you have to consider this kind of chunk. Like this way, and so on. Okay, so all those coarse grain. So you just average over all the microscopic information to the macroscopic information. That is, so microscopic means low energy. So essentially we use Heisenberg principle, Heisenberg uncertainty principle, that the del x, del p is roughly h1. If this is small, the momentum becomes big. So therefore, if the microscopic information means the high energy. If you have a microscopic information, this h1 is a high energy Hamiltonian. High energy Hamiltonian. But if you just integrate over all possible configuration, you get the low energy Hamiltonian. That's the so in this way, one can just have a coupling constant G2 and so on, G3 and G4. Okay, so that's how you get. So that's the renormalization group. And from now on, we call it RG flow. RG flow. So therefore, so if you have a space of coupling constant, whatever. So this is the, say, G, and then whatever, lambda. Lots of coupling constant. Not only G, but okay, lambda or mu or whatever. Coupling constant. So coupling constant, you start with around this point. This is point 1, H1. So then if you just integrate over, you may just H2 and so on. And you just H3 and so on. And then you may just move the space of quantum periphery, or space of a coupling constant, or space of Hamiltonian by just averaging over. So that's the concept of renormalization group flow. Okay. And then in this process, at some point, you may just even Gn can be equal to Gn plus 1. Can be. Can then Gn plus 2 and so on. Even if you just average over many blocks, so G may be fixed, fixed. In this case, G star is called a fixed point. Okay, fixed point. If you encounter this point, if you reach to this point, this is the series that even if you integrate over or like even if you look at the microscopically or macroscopically, I mean coupling constant doesn't matter. So which means it's a scaling invariant. Okay, scaling invariant, series scaling invariant. So this means that the theory is described. It's believed to be described. CFT. So this is the. Yeah, let's look at an example. Very simplest example. Okay. Simplest example is the one-dimensional Ising model, classical Ising model. Okay, H is equal to okay, and then we have the so S1, S2, S3, S4, S5, S6, and so on. S4, S5, S6, and so on. And then we sum over, let's say, like this way. Sum over all possible spin like this way. Like this way. And we average over like a 3 spin side and so on. One can do that. Okay. To do that, we recall that this Boltzmann weight of this one, Boltzmann weight of SI is equal to E to the K, where K is equal to K is equal to J K times. Like this way. Where B is equal to tan tan. So this is just the manipulation we already we already saw to see the spin configuration. To the model. So this Boltzmann weight can be written like this. Okay. And now we look at the following thing. So let's average over. So let's rename. This one is the middle one is sigma 1, and this one is sigma 2, and this average of S3 and S4. Okay, the configuration S3 and S4. That's we can do. So to do that, we look at this. So if you look at anyway, so Boltzmann weight of K is sigma 1. This one, so it's a local configuration. So sigma 1 is this one, S2 actually. Sigma 1 and S3 and S3 and S4, S4 and then sigma 2. Sigma 2 is S5. And then we just average over S3. So all possible configuration for S3 and S4, which is plus minus 1. Okay? Plus minus 1. Which we just average over this. Do the coarse graining for this one. Okay. Just keeping in the middle. That's what we can do. And then just plug this one into here. Okay, so then cosh K and the cube and 1 plus P sigma 1 S3. Like this way. Like this way, and then you just need to sum over. S3 and S4 is inside of plus minus. Okay, so it's just this one is just this one times cosh K. This one is this one times cosh K, and this one is equal to this one times cosh K. Okay, so that's it. And now we sum average over S3 and S4. Okay. So now, if you do the average over S3, S4, if you have like cross term, like this times this times this is equal to have a S3. If you average over S3, you get 0. Okay. So at least you need to have an S3 square to have a non-zero answer. It's the same thing. S4 square also you need to have. Okay. Otherwise, I mean, if it is linear, if you average over plus minus, you get 0, right? So S3 square and S4 square, you can get is this multiplication of these 3 terms. That's the only non-zero term you will get. Okay. Otherwise, this times this one, S4 will remain. S4, linear in S4. And this times 1 is S3 will be linear. Linear S3. So that you get 0. So all the cross term you give it 0, but non-zero one is something like this one. sigma 1. Oh, sorry, Q. So if you just multiply them together, you get this one. Okay? Is it okay? So therefore, what you get is that, so this is the can be understood as a coupling constant because I mean K is essentially the parameter of the space. Capital K is the parameter of the space. B becomes BQ once it's average over this adjacent average of adjacent spin like this one. Okay. Like this. So this is the new coupling constant, and this is microscopic in terms of microscopic coupling constant. So this is the so this is the renormalization RG flow equation, and the fixed point is essentially B star is equal to 0 or 1. Okay. B star is so. When B is equal to 0, B tilde is also 0. So that's why it's fixed point. When B is equal to 1, B tilde is also 1. Okay? So therefore it's a fixed point. Essentially this means the temperature is 0. No, temperature is infinity. Okay, sorry. B equal to 0 means the high temperature, and this means the T is equal to 0 for temperature. Right? So B is defined like this way. B is defined like this way. So therefore, so B is equal to 0 means the T goes to infinity, and B equal to 1 means the T goes to. So that's the fixed point of the Hamiltonian. Okay. And new Hamiltonian system, so the new Hamiltonian, you start with this Hamiltonian, but now we have this kind of Hamiltonian, so that the H, so you have some constant which is not important, minus J tilde, sum over sigma I. Like this. Okay, so that's how you get. So essentially you have the same Hamiltonian, but it was with different coupling constant. Okay. J tilde. So this constant is not important actually. This constant you can always shift. So I don't care about this. Fine. So that's the simplest example. And the J tilde, if you want to know the J tilde, is the K times T times inverse times K cubed. Okay, so that's the equation you will think. Any question at this moment? So that's the rough idea of the renormalization group. So as you can see, since we already average all the information, you cannot go this process from here. You cannot restore the information of H1. Usually, this direction you cannot do. Okay, this direction irreversible means that this direction you cannot restore the information usually. So therefore, you have to be careful. This is not group because there is no inverse of this process. Okay, so this is not group. Okay. So now let's look at the beta function and column semantic expression. So start with some fixed point, and you can just integrate over all possible 2 pi GA OA. Operator of A is X. I mean, here I can do it in the general dimension. General dimension from okay. So, I mean, you can only generalize that. It's super easy. I mean, just change this one to D, this one to D, But let's fix 2 dimension at this moment because for the sake of simplicity. Let's look at the. I mean, if you, this constellation can be generalized at any dimension, higher dimension, more than 2. But I mean, for the sake of the simplicity, let's consider 2 dimension. So this is the conformal field theory action. Let's consider. And from here, so there is space of the G1 coupling constant, G2 coupling constant, and so on. Let's suppose this one. This point is when G1 and G2 is 0, this point is CFT. CFT. This is S star is the action for conformal field. And then you can perturb the theory. So this is called perturbation. Perturb the theory. This is a perturbation term. And this is always some operator. By introducing coupling constant, introducing operator to the action. This is for 1 direction, this is for 2 direction. Like this way. And then we'll see what's going to happen. Okay. So we'll see what's going to happen once we introduce this perturbation term. And do the suppose that the scaling transformation d lambda. So this is the scaling transformation. Then this action is the transform like this way. So sound. Okay, so that's how it scale. So dx will give you this square here, and this operator has a scaling dimension lambda, so that the 2 minus lambda will show up in the exponent. So these 2 coming from this d square x integration term, and this lambda coming from this operator. Okay. It's a scaling, so that lambda is delta is a scaling dimension of operator O. Right, and then and suppose this d lambda is very small. So d lambda is very small, and it starts the invariant under the scaling transformation. So therefore, this can be written down. So I just keep only like a linear term in d lambda. Like this. Okay. So that's a linear term. So I only just do that the Taylor expansion and look at the linear in D lambda. So this is how the scaling transformation will map to the will map. So I think then. So on the other hand, scaling transformation is generated by the net current. Net current is this scaling. So therefore, so the scaling transformation is given by d lambda is d squared x t11 plus d22, like this, which is equal to s minus d lambda d squared x 2 pi theta x. So the theta is the up to some factor is just t mu. Diagonal part of the source energy tensor. Okay. So that's the scaling transformation is generated by. Okay. So therefore, if you compare between these two, you will realize that the theta of x is equal to minus lambda beta a g. Maybe I should write down like this way. Minus 2 minus delta A and GA. Okay. Like this. That's how it works. And we call it this one is equal to beta G. So we call it beta G, which is just a D line D. How G would depends on the scaling of lambda. G is lambda. We call so this is called beta function. This is called beta function. If you solve this equation, you will get the G A is a linearly 2 minus delta A of G. Lambda. Like this way, the scaling lambda. So if you solve this one, so it's easy to solve, right? So this 2 minus delta A G dg d lambda. So therefore, this is 2 minus delta A d lambda and dg over g, which is the d log g. So therefore, you can just integrate over this equation to get this one. Okay, is it okay? Fine. So therefore, if delta, A is less than 2 coupling constant in the, so G will increase. G will increase. G will increase by if you scale lambda. So if you scale lambda, okay. So lambda is it becomes coarse grain. So if you do that, G will increase. Delta A is greater than 2. This is decrease. Okay, decrease. Delta A equal to 0. So this is the We don't know. So this is linear. So if you only look at the linear perturbation theory, so if you only look at the linear term in lambda, it's how to say, the coupling constant does not change. So that's the. So therefore this one. So in this case, G will increase, which means that if you go to low energy, it becomes coupling constant bigger and bigger. Okay. Whereas if delta is greater than 2, the coupling constant become the smaller and smaller. So therefore, this one is called relevant and irrelevant. Okay. And delta equal to 0 is called marginal. Fine. So if you look at the space of a coupling constant, so if you have the like a G star is the, so when beta G star is equal to 0 means the this is called the fixed point, and irrelevant means that the irrelevant deformation always just flow to the fixed point G star. Okay. The irrelevant deformation, even if you just deform the theory, it just go back if you just integrate over the high energy scale. So this is irrelevant. Sorry. Irrelevant deformation. On the other hand, if you just look at the relevant deformation, this is become coupling constant bigger and bigger. Okay, so this is relevant deformation. If you turn on relevant deformation, you won't come back to the original CFT because the coupling constant bigger and bigger. The theory will change to different theory. Okay, so that's what's going to happen. And in fact, so the middle guy is most how to say, subtle one. So this one is classically, so that in the linear order, classical linear order is that beta function. So the beta function is 0, but quantum mechanically, you never know what's going to happen. So when delta equal to 0, but quantum mechanically, beta can be beta function can be 0 or if you include quantum mechanically, you can have the non-zero beta function. Non-zero beta function. In this case, this one is called marginally relevant. Marginally irrelevant. And this is exactly marginal. So that's the so but if you if you take the QFT course and so on, beta function receive like 1 loop correction, 2 loop correction, and so on. Moreover, if G is very big, non-perturbative correction will become important. So quantum mechanically, beta can be receive lots of quantum correction in addition to this one. In addition to this classical scaling. But if you include all the quantum correction, beta, if it is negative, it's marginally relevant because beta function is negative means smaller. And the marginal relevant becomes the bigger and bigger. And beta, so this is truly quantum mechanical CFT. Okay, so that's the exactly marginal. So that's the notion of wave function and so on. And then we just introduced so-called column semantic equation from that. But column semantic equation is the correlation function. How correlation function behave under RG flow. Okay. Column semantic equation. Semantic equation. I forgot how to spell column semantic equation. Oh, sorry. Semantic equation is the RG flow equation for correlation function. Okay, so that's the we're going to learn. So correlation function is the, as I mentioned, phi 1x, phi nx, and can be understood as the phi like this way. So and then variation of the alpha phi I can be understood as like this way. X mu, partial mu, plus delta I, and phi I. Under scaling transformation. So that's, we already knew how they behave. So therefore, for Takahashi identity for scaling transformation become like this way. So the maybe I should write down the index. Okay, so that's the word Takahashi identity. So word Takahashi identity. Identity or scaling transform. Okay. So, but if you look at so now S is here. Okay, so S is the I already erased. Or did I erase? Oh yeah, unfortunately I erased. S is this one is S star plus what was that? Sum of A d squared x to phi g GA, OA. Okay? That's the assumption. So this S has the conformal fixed point action plus some perturbation term. And suppose let's look at how this correlation function will behave under this derivative with respect to this coupling constant GA. Okay? Phi 1, phi n. Okay? Let's consider this one. So here, I just assume this is sum of the beta n, like this way. Then this one, so if you look at this derivative can, if it acts on this the action term, you will get the following term. You will get that sum over a beta a b square x t phi o ax like this. Because I mean, so if you act a derivative of del GA, you just this derivative see this coupling constant and bring OA out of the action. Okay, so therefore this one. On the other hand, we can have this the quantum mechanically phi I, this phi I of x may have a dependence of GA. So I call it B. Like this way. So if you consider this kind of so quantum mechanically, the phi can depend on G, so that the this one will give you the following term. Like this. So that's the how this derivative with respect to coupling constant will act. Oh, sorry. Sum of. So here, sum of the A. Like this. And then, so we can use this identity, and this identity. So this identity, so this theta of x is equal to minus sum of beta a and OA, right? So we can use this identity to rewrite this one. So this part can be written as follows. Like this. Like this. By using this relation over this. So now we can compare between these two. To get rid of theta of x. So once you do that, so you will get the following equation. This way, acts on phi 1, phi n, times A, and then minus sum over A, delta GA, phi 1, delta phi is equal to G. So that's how we get this. So this is called Cannon semantic equation. This is called Cannon semantic equation. And the important thing is that this is classical scaling dimension. This is classical scaling dimension. On the other hand, this guy will give you quantum correction. To the classical scaling dimension. So and total thing is we call it gamma hat I. In total, okay, maybe I should write that total thing. This one is really high. Gamma hat I. So that's the how it behaves correction function under the scale. Under scale. So therefore, under scaling transformation, so this x mu del mu here is just scaling transformation. We'll give you some quantum dimension with a quantum scaling dimension is equal to this derivative with coupling constant with beta function. So that's quantum mechanical. So this is called Collins simultaneous. Okay, so that's the also this quantum correction is called anomalous dimension. Anomalous dimension. Because I mean it's a correction to the classical scaling, so therefore it's called anomalous dimension. And using this Collins semantic equation, we can derive so-called Zamolodchikov figure and so on. But before going that, let's take a break. So if you have a question, just tell me. Feel free to ask me. Okay. So let's take a break, 10 or 15 minutes.重间化群，中文的发音真的非常难。重简化群，重简化，重简化 ，OK， 重简化群，不是群 ，OK。This is Joshua. It's so difficult for me. 重简化，Yeah. Always like a repeat and yeah. So I 用中文上课很远。重简化去。 this.
I want to ask
Yeah.
the relation between 2D safety and the 4D Yang-Mills incident just mentioned in the class.
Oh, okay. So this conformal block. It's so conformal block. You can compute the 1 plus some factor C 2 times alpha, alpha times Q plus Q squared plus Q to the, so Q is a 0, 1, infinity, like this way. Q cube and so on. So like this way. So this is a conformal block. But on the other hand, so in 4D, 4D n equal to T supersymmetric Yang-Mills theory. And then SU2 gauge group, and then the four primary field, corresponding 4 primary field, there's 4 quarks you can include. You can include the 4 quarks. Then here you can just have so-called so F mu mu, the configuration of this epsilon mu mu cross sigma F cross sigma. We can consider this kind of gauge configuration if you look at this gauge configuration.
So this is the instant.
Yeah, instant. This is a gauge configuration. This gauge configuration is not it's not empty, so it has some finite dimensional modulus. It has, so if you have the so it's R1 plus 3. So therefore, the instant means they really instantaneously appear in this space-time field. So it has the something called the position, and also what was that? The size of the instant. So it just parameterizes these it's called parameter modular space. And then one can just do the so-called modular space of the instanton. So instanton, and the instanton. So this is the instanton number 1, but the instanton number can be like an integer. It's essentially it's describe a first one tracking number of the principal G bundle over R4, R1, 3 or S4. It's instanton number, and then so instanton number. And here, so this is kind of like some kind of like the manifold or space. And then you can just consider so-called conformality theory of this manifold. And you just consider so-called anyway, so there is some from this conformality theory one can construct so-called partition function, instant partition function. And this instant partition function has become the same as this one. Becomes the same as this. There's a procedure to compute this instant partition function. So this is due to necklace. And that is equal to this one. This one.
The 2D theory should be the Liouville theory.
I mean, if you include one loop determinant, so conformal block only depends on Virasoro algebra. So any 2D CFD with Virasoro symmetry all give you the same conformal block. Except this conformal dimension depends on primary field. That's it.
Why for AGT correspondence it must be in Liouville theory? And
I mean, it's a one loop determinant depends on the theory, 2D theory. So this structure constant C So the correlation to compute the correlation function, you need to include structure constant like a structure 3-point structure constant. This depends on the
I see.
2D theory, and that is really, in fact, it's called Z1 one part, and that needs to be zero. And also, I mean, it has to be some non-rational because I mean, here this conformal dimension needs to be continuous parameter, continuous. But if you consider the minimal model, all the conformal dimension is fixed because it's the only finite Mani's parameter and a rational number. But to have the continuous parameter here, it has to be irrational conformal field.
Yeah. I see. So it's just the lower parameter.
Yeah, Levy momenta.
I see.
So here we need to impose the supersymmetry.
Yeah, you need to have a supersymmetry to define this to define is something called the instant partition function. Otherwise you won't get anything meaningful. I mean, so if you don't have a supersymmetry, computation is too difficult.
So the one determined is given by the supersymmetry.
Yeah.
So the vocabulary should be. So the Fourier theory is defined on the class space.
Yeah, class space. 重整化。Okay, let's get started.那我们到去了，关联函数函数的重整化范畴，被称为color semantic 的范畴。那我们用这个范畴导出 Zamolodchikov C 定理。Okay, so that's the goal of the second half of the lecture. Okay, before then, let's look at the meaning of this gamma. So this gamma hat. What's the meaning of this gamma hat? This gamma hat, this Sailor has the scaling dimension has to be 2, equal to 2. And this cannot be changed even quantum mechanically because this is a negative current of the scaling transformation. So it cannot be changed. So this has a scaling dimension 2. To have this scaling dimension, let's look at this gamma hat acts on Sailor. As I mentioned, this gamma hat is that will give you scaling dimension, including quantum correction. It has to be, but it has to be 2. And if you look at this action, sorry, what? Oh yeah, it's okay. So this one acts on the d hat, del hat plus product of beta a del what's that del GA? Because of this BIA is just how this derivative with respect to this coupling constant that acts on Sailor. Okay. And we know theta is can be written in terms of this beta times OA. So therefore, just plug that into here. Like this one. Okay, then so this is the this derivative can act on G, or entire thing is actually gamma acts on O. So therefore, so this one is equal to the sum over beta B gamma hat O B plus sum over N and B and O. Okay, so that's the Howard axiom. And this should be equal to 2 times minus sum over beta A, beta B, and then O B, like this. Has to be, because when it's just theta acts on, so gamma acts on theta has to be equal to 2 times, so this is equal to 2 times theta. And if you compare between these two, we can understand how gamma acts on O. Okay? Compare between these two, how gamma acts on O. So this gamma acts on O. To satisfy this equation, gamma of OB has to be equal to so OB acts on gamma OA gamma, so 2 times delta AB minus delta beta A delta B. Okay. So that's how it works. I think it's better to do it the opposite. A, B, B, A, B. That's okay. Yeah. So in that case, if you plug this one into here, so this part cancel with this one. Okay. This part will cancel with this one, and then 2 times delta AB will give you this time. Okay, will give you this time. Okay, so this time this part cancel with this one, and what's left it will give you 2 times this one. So this is how gamma acts on O, and we know the linear order. So the classical this should behave like 2 times delta B times GB. Like this beta. So this is the classical. This is classical beta function. Beta function. So if you plug that into here, so this is okay. Let's look at the classical. It's a classical, and plug this one into here. And what you find is that this is exactly delta A O A. So that's that. Okay. So therefore, classically, this gamma hat will give you just classical scale. But since with the beta we receive quantum function, one loop, and so on. So this quantum function, so usually this will give you like a whatever some number times g to the square term and some number, the g to the cube term. So this is 1 loop correction, this is 2 loop correction, and 3 loop correction, and so on. Those are the quantum correction you will receive. That will change how this scaling dimension will quantum mechanically. Okay. So that will give you the change of the scaling dimension quantum mechanically, delta to something non-trivial here, something non-trivial. Okay. So therefore, I mean, here I did very ad hoc way. This theta, sorry, not theta, phi will depend on G, depending on Z, and its derivative will give you some non-trivial action on B, and that will create some anomalous dimension. But if you look at this, action of gamma on operator O, it's clear that it's received the derivative with respect to beta, with respect to coupling constant. That clearly receives root correction. So that's what you learn in quantum field theory. Actually, GHP theory. I think this semester Gujani provides this QFT2, right? QFT2, and then you compute beta function, right? Most likely I pretty yes. Yeah. So you know how you compute this quantum correction at least one level order. I also never done quantum correction computation in two level. Only I did also one level. But anyway, so even one level that will give you correction to delta. So that will give you this anomalous dimension. So therefore, the classical scaling will often receive quantum correction. That is called anomalous dimension. Okay. Okay. Any question at this moment? Now, then I will move on to Zamolodchikov c-theorem. So Zamolodchikov c-theorem will tell you that the following thing. So I mean, in 3D quantum field, if you study the two-dimensional quantum field theory, the contribution of Zamolodchikov, actually Zamolodchikov are brothers actually, but one of them has passed away at an early ages, and now I don't remember. Yeah, so the other who now in Stony Brook. So. And anyway, so if you study this two-dimensional quantum field theory, Zamolodchikov and Cardy's contribution is significant. I mean, I highly recommend to read one of the papers Zamolodchikov or Cardy in the 80s, and the Zamolodchikov c-theorem one of milestone in the study of quantum field. So that's what we're going to learn. So Zamolodchikov, let's write down statement at least one. Number one, if you assume the rotation series theory, two-dimensional theory, 2D theory, is the rotational invariant. And number two, you assume the unitarity. So the theory is unitary. The theory is unitary. And number three, and the energy momentum is conserved. Energy momentum is conserved. Okay? So that's three assumptions. It's a very like a general assumption. Almost all the two-dimensional physical quantum field theory satisfies these conditions. Then the conclusion. So these are assumptions. The three assumptions. So there exists a function C, which is non-increasing under R0. Seems like I already did. But it's good to. So we know that if you have a conformal field, there is like a CFT point here, and there is some, how to say, irrelevant deformation. We will just map to like this way. Irrelevant deformation is mapped to like this. Okay. Like this way. And then the C. So this in two-dimensional theory, C function, one can consider C function such that around this RG flow, around the RG flow, C is never increasing. So C is just keep either constant or decreasing. Or actually it's decreasing. Except the CFT point. CFT. Okay, so that's the statement of the and moreover this C so this C function. So this C depends on scale R and also like some coupling constant G and so on. So this is the scale or energy scale. Scale of the theory, and this is coupling constant. And then at the fixed point, at CFT fixed point, the C is in fact is equal to central charge. Of the theory. So that's the statement. That's the statement of Any question at this moment? So that's the statement of the c-theorem, and we will derive from now. So let's begin the assumption number 3. The assumption number 3. T min is equal to 0. And this one will so this one can be written as follows: del bar t plus 1 over 4 say equal to 0, or del t bar plus there is equal to 0, like this. So recall that this t is t z bar plus del c tcc. Okay, so that's what you wrote. What I wrote here is equal to 0. Can be written like this, right? If you do the proper normalization and so on. Okay, so this is equal to this, and also the opposite is like a tc plus del c bar. Sorry, t bar c is equal to 0. This one becomes like this. So it's just a rewriting of the define this component by 1 over 4 theta. Okay. Okay, so those are a combination of the and now also here t. So T is no longer holomorphic. So theory is no longer conformal so far. So we just assume any two-dimensional thing, quantum field theory. So therefore, to the QFT. So it's not conformal field theory. So you don't assume the holomorphic factorization of stress energy tensor. It has a z and z bar dependence. Also, theta has the z and z bar dependence. Okay, and then, but this one is coming from. So this one is, as I mentioned, so t z z, right? Up to some factor, 2 pi or something like that. And this one is minus 2 pi t z z bar. Or minus 2 pi t z bar z. Sorry, I think it's pi. And then t bar, t z bar is equal to minus 2 pi t z bar z bar. So now so this holomorphically depends on 2, 0. And this is 1, 1. And this is then 0, 2. Holomorphic spin dimension. So therefore, if we consider the correlation function of the TT correlation function, so assumption will tell you that this will give you the scaling is always like this way, and T, sorry, F, and ZT bar. So that's the assumption. Because I mean, so here I use so this is the assumption 3, and here I use the assumption 1. So assumption is the rotational invariant. So therefore, so here the correlation function has to be only depends on the dependence of R in here. So it's just absolute value of T. Okay. So F is a dimensionless quantity because I mean T has the holomorphic 2-0 weight. 2-0 weight. So 2-0 weight, if you have so you have 2-0 weight, you get the one of these T0 points. So this part will come from the scaling dimension of this TTOP, not OP, TT correlation function. So likewise, and then the numerator here is dimensionless now, not dimensionless, and it only depends on radius of this or distance between these two. So therefore, because we assume rotational invariance, and this is dimensionless because I mean, so this theory to the QFT is not. I don't assume any conformal invariance. So therefore, it can have any like a dimensional coupling constant, like whatever mass or whatever dimensional coupling constant, and then this Z is of course has the scaling mass dimension 1 over minus 1 mass dimension, but I can cancel with some other coupling constant to make it numerator to be dimensionless. So that's assumption. So but I just hide it. I only assume looking at the distance. And then okay, I don't have enough space to write down. Unfortunately, I should write it here. So this is new denominator comes from the scaling dimension of TT correlation function. This is f of z, and I call it dTZZ. Like this way. Like this way. Oh no, sorry. square, and then h. Okay, so this is a valid assumption one can make. So here, all denominator come from the homomorphic weight of the energy tensor. This energy tensor, and the numerator is only dimensionless or all dimensionless. That depends on radius or distance between these two operators. Okay. And then, so this is the assumption. I use assumption 1, and then also, so assumption 3 will tell you that the dou bar dz equal to 0, like this. Okay. So that's the energy momentum concept tensor. And if you use, so from here, so this is the homework for incoming weeks homework. So from here, if you use the notation z dot f dot is equal to something like a zz bar f w dot zz bar. So that's the notation I use. So essentially, z, if you write down r, so this should be r squared, derivative of r squared, f of r squared. So this is what it means. Okay. So I mean, zz bar is equal to r squared. So radius r squared. So this is the dot notation I introduced. Then from here, so this is the exercise for homework for this week. I mean, just computation. I mean, I don't want to do the computation in front of you. It's just tedious. That's it. So become like this. You will get this. And also, one can consider the following equation. Say 0, 0. Is equal to 0. Okay, so from here, equal to 0. Okay, so this is also home. And from there, we can get rid of g. So if you compare these two, one can get rid of, so okay, so let's consider this one is star and the double star, and we can do the following thing. So the what was that? Times 4 over 3, and then minus will give you the following equation. 2f minus g minus 3 over 8h is equal to, and then r squared, the other r squared is equal to minus 3 over 4h. So that's what we can, okay. So, I mean, essentially, yeah. And we call this one to be equal to defined by C. Okay, so we call this one to be, we define this C. Exactly the C we want to have. This one. We want to have. Okay. Now we use the assumption 2. We use the assumption 2. Here, assumption 2 tells you that this h is the theta correlation function. Okay? So unitarity will tell you that this. So theta correlation 2-point function. Unitarity will tell you that h has to be positive. Okay? Unitarity. It cannot be negative. Unitarity theory. So therefore this is positive quantity. So therefore this has to be negative because you multiply minus times 3 over 4. So this is assumption 2. I use assumption 2. Okay. Now we use all the assumptions. So therefore this function c, if you take the derivative with respect to scale, it's always negative, non-positive. Okay, so non-increasing. Okay, non-increasing. So that's why we already found the first statement. We already found the first statement. One can say much more than that from this constellation. So this means that the C no increasing, and furthermore, okay, so C is like this, okay? No increasing function. And now you can say much more than that. So now we use the Cullen semantic equation. Cullen semantic equation, which is as follows. So C is not C is some function. Okay, C is function coming from numerator of this 2-point correlation function. Okay, so therefore it's Cullen semantic equation. Do not. So there is no scaling dimension. So as I mentioned, so this is dimensionless. These are dimensionless quantity. Therefore, Cullen semantic equation for dimensionless quantity is R del R minus beta A acts on C R equal to 0. So that's Cullen semantic equation for this function C. Okay, now so this one C. So we already knew that this one. So R square del R square is equal to C is equal to minus 3 over 4H, right? 3 over 4H. And then we can use this relation. So we can use both relations. For instance, how can you get it? So H is equal to R squared theta R theta and Z. So that's the R to the fourth. Sorry, R to the fourth. trigonometric h, so this h is this one, and this denominator is equal to r to the 4, right? Is r to the 4. So h is this one. And then you can just plug this one into, and here we can do is that the chain rule, so I can use the chain rule to show, sorry, I got confused. Delta r squared is equal to, delta r is del r squared, del r. So you just do the Leibniz rule, chain rule to find this is equal to 2r times delta r squared. Okay, is it okay? Is it okay? I'm doing correct calculation, yeah? And plug this one into here. Then this will become 2 times r squared delta r squared. Column semantic equation become like this one. Is it okay? So far. And we know that this one is equal to this one, right? Is equal to this one. So plug that one into here. And then what you get is that this, so from here, and the h is this one. Okay? H is this one. Okay, and this is equal to r to the 4th. Like this way, sum over a and b. Okay. So we already knew that the Sayer. So Sayer is equal to sum of over a, like this one. Like this one. So that's what we already found. Okay. Now plug this one, everything into the column semantic equation and to see what this really equation means. Okay, what this really equation means. Sorry, I told you this is wrong. So this is a minus sign. Minus sign. But if you have a 2 Sayer, so minus sign will cancel, so that this is okay. 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 So that's the case. And then now I can erase some of the part. Where can I do this? Maybe I can erase here. Maybe. Because I want to show that the 1, 2, 3 will give you this function c, and that is the non-increasing. So I can erase this one. This part. So now, so here 2 times minus 3 over 2h. Okay. Minus 2 times h minus sum over a, beta a, delta ga acts on c of r. Sorry. C, acts on C is equal to 0. Okay, so now we already showed that the so this is equal to this one, and then this you can plug it into the, you get this one, and now h is equal to this one. Okay. So here h is equal to this one, so which means that the is equal to minus 3 over 2 h. H is this one, sum of r to the 4th. times beta A, beta B. Okay, that's what we have. So now I already used the Einstein convention. So sum over Einstein, I already erased sum over A or something like that. I use Einstein convention. So this is the case. And now, so we call this one two-point function. So this part, we call it the metric. So this is, I call it G and E. It's called Zamolodchikov metric. So if you have operator deformation, so this operator O will define some perturbation of the action from the conformal filter. So this is the two-point function will give you a metric, and that will give you so-called gradient equation. So this one, therefore this one will become beta A delta GA of C is equal to and from here, so assume this G has an inverse. So if you have G has an inverse, this equation can be written as follows. So the function of A is equal to -2/3 GAB inverse del C del GB. So that's the equation one can write. Okay, so that's the equation. One can write. So this is called gradient equation. This is gradient equation. Gradient flow equation. So often you encounter the following thing. So, okay, so given a function, given a function f or function that is manifold to R, one can always find the gradient vector field. Often just people write grad f or like this way. Like this way, nabla of f, such that this one is equal to GAB del f del xb and del xb. It depends on notation. Some people put the minus sign and so on, plus minus sign depends on notation. So this is called gradient vector field. So gradient vector field is, for instance, if you have a manifold or whatever, say torus. Say torus. Okay. Say torus, like this way. And then the function is, let's call it the height function. Height function means that if you write down function, so this point is mapped to this R. It's like this way. So this point is mapped to the height function. So this point is mapped to this. So this one is called height function f. F is a height function. And then gradient flow is literally the flow equation from top to bottom. So so critical point is essentially the derivative of f becomes 0. So there are 4 critical point here, and the gradient vector field is something like this one. Anyway. like this way. Like this way. Okay, and then there's often like a field is something like this way. It flows. Like this. So these are gradient for equation. So these are gradient for equation. Anyway. Okay, so that's a gradient flow equation. So likewise, this this equation is also the c. If you scale c by 2/3, this is exactly gradient equation with the g is the inverse of Zamolodchikov metric. So. So therefore, beta function in 2D QFT is realized by this gradient flow equation with Zamolodchikov metric. So that's the consequence of this column semantic equation. And then C is the most function. Okay, this is anyway. C is the most function. Most function. I'm not going to define. Okay, most function means that the let's see. Most function means that the. Okay, it's better not. Anyway. Okay, so most function at the critical point means at the critical point C Hessian C is something like this one. It's given GA del GB is the determinant of this one is not zero. It's non-degenerate. That's what I mean. So that's the definition of most function at the critical point. This Hessian, it's called Hessian. So if you do the second derivative with coupling constant, you have a matrix, and that is invariable. Means non-degenerate means invariable, or determinant is not zero. And the C is mole function. So this means that now we can consider this space of coupling constant as a manifold, and the C is some function from this space. So this is space of coupling constant, or relevant deformation. From here, it's everything in relevant deformation. And if you consider this one, so it can have like a very non-trivial form of the like a manifold. It can be not as simple as like this torus. It can be like a higher dimensional manifold, more how to say, topology and so on. But anyway, so this space of coupling constant can have a manifold structure, and C is just function from the most function from this space of coupling constant to the R, and then this beta can be realized as a gradient flow of this most function. Okay. Okay. And moreover, so that the fixed point, at the fixed point, beta function is equal to 0, right? So therefore, this one, left-hand side is equal to 0, which means that the right-hand side is equal to 0, which means that this, at the fixed point corresponding to critical point of the most function is the critical point of most function C. Most function C. Critical point means derivative is equal to 0. So which means that the whole critical point. So this is the critical point, this is critical point, the whole critical point. Because I mean, if you derivative really of this height function is 0. So the whole point and the critical point, those are the fixed point of this those points correspond to CFT fixed point. CFT fixed point. And then, as you can easily see from here, here everything goes downwards. So everything, so all the deformation become relevant deformation. But if you look at here, it's just outgoing to two direction, but inflowing to from two direction. So the two direction. Okay, so one dimension of this direction is relevant coupling, but this is irrelevant coupling for this fixed point. Okay. Do you understand what I mean? It's inflowing from one, how to say, two direction outgoing to the two direction. So which means that this direction is irrelevant coupling for this perspective, and this direction is relevant coupling this perspective. But if you look at this one, everything inflowing. So this means inflow. So therefore, this means that all the coupling deformation is irrelevant. Everything, even if you deform, you just come back. Okay. You just come back. Okay. So that's how it works. For these. Critical point becomes CFT. And furthermore, at this point, unfortunately, I already erased at the fixed point of C, and then here I use define F like this way. So I define like this way, and the fixed point at the fixed point. So this becomes TC. It's everything holomorphic. Because it's at the CFT point there is a conformal symmetry that will just map the holomorphic factorized. So therefore this will become C over 4, C over 2, D to 4. Okay. So therefore at the fixed point. Which means beta equal to 0. Okay? C over 2. So therefore F. So this means F of Z is C over 2 at the fixed point. So it's just constant, which is the central charge of the theory. And moreover, so the other, at the fixed point, the other part will become 0. So from here, T of T C T bar and theta. So this is G of something like this here, right? And H of the, anyway, I'm not gonna write that. So this will give you G and H, but at the conformal fixed point, theta equal to 0, because I mean, trace, it has to be theta is proportional to 2 pi T mu. So this should be 0 at the fixed point. Okay. So this should be 0. It should be traceless because it's a conformal field theory. So therefore, so at the fixed point, G is equal to 0 equal to H. Okay, so that's what's going to happen. And of course, H has to be 0 because I mean it doesn't flow anymore. So C is already fixed because central charge. Okay, so that's the. So recall the C equal to 0, and if you recall the definition C, I'm going to write down here. Definition C is equal to 2 times F minus, what was that? G minus 3 over 8H. Okay? And at the fixed point, G is equal to H equal to 0, and F is equal to C over 2. So therefore, this should be at the fixed point. Fixed point, this should be central charge. Because G equal to 0, H equal to 0, F is equal to C over 2. So therefore, small c over 2. So therefore, this is central charge. Okay. So that's exactly what we want. Okay, so that's the beautiful theorem by Zamolodchikov. In the it's a really milestone in 1986. Beautiful. It's so therefore this function C somehow control the information about the RG flow. Control the information RG flow, and moreover, what's really happening is that the always the CUB has to be greater than CIR. Okay. So along this RG flow, so RG flow go from top to bottom. So of course that now it's literally function C is really top to bottom. So therefore it's always decreasing, right? It's always decreasing. So its body of C is really this height actually. Height. So therefore it's flowing from top to bottom. It's really like a RG flow decreasing. So therefore CUB has to be CIR. So therefore often this function C encodes degree of freedom. Degree of freedom in 2D quantum physics. Degree of freedom. Because going from UV to IR, you have to integrate over all higher energy mode. You have to integrate over higher energy mode. So you somehow you just do the coarse graining, right? So we already know that the RG flow is coarse graining from microscopic scale to macroscopic scale. Okay? That's we already learned. So under this coarse graining, lots of information will be lost because we average over everything. Okay? We average over everything. So therefore, how to say? The information is become less and less, and the degrees of freedom are less and less. Therefore, this C is physically encodes the degrees of freedom in quantum physics. Okay, so that's the So that's the one way to understand. One way to understand this function C in two-dimensional quantum field theory, and this is how you understand the. This will give you crucial information of RG flow in the two-dimensional quantum field. So this is the two-dimension. There is some four-dimension version. This is a two-dimension. The four-dimension version is given by ski and then swim. Hey, I forgot how it's spelled. So there is I think I should write down. Yeah. And then it should be I. Okay. Sure. This C appears so-called anomaly coefficient in 2D. I mean, the C is the somehow stress energy tensor of C is the 1/12 C with R, like this way. I forgot it's a minus sign, plus minus, I don't remember. So this R is a curvature. If you put the 2D theory in curvature, somehow there's a traceless T mu, T mu is no longer zero. So no longer zero. It's proportional to the background curvature R. So R is a background curvature, and proportional coefficient becomes C. So that's how one way to see the central charge into the theory. So this is called Y anomaly. And in 4D, we can do the similar thing. So T mu is proportional to A times, I forgot, Euler number, and then some number, I don't remember, plus some number times C of Y, tensor, like this. So there are two central charges will appear in 4D. And this A and C are non-increasing, so it's decreasing on the RG flow. So that's what these two people will show in, I don't remember, like a 2010 or something, 2010, 10-ish, something like that. And 60 we can have similar statement, but with supersymmetry, And then here alpha, omega, gamma, delta, there's a four central charge will show up in 60 in supersymmetry theory, and that is non-increasing on the RG flow and so on. That is done by Cordova, Dumitrescu, and the Intrigator. So that's the, yeah. Anyway, so those are even dimension. Even odd dimension, there is some similar theorem. It's called F theorem and so on, but I'm not going to go into the detail. Okay, so that's the story of the Zamolodchikov theorem. Any question at this moment? Okay. If you want, I just give you some brief introduction to the next lecture. Brief. So I don't think I can. So only 15 minutes left. So I don't think I can write down anything about. So now, Conformal and Zamolodchikov proposed the more, again, interesting correspondence in the theory. Okay. So let's consider a lambda model, two-dimensional lambda model. Lambda Ginsburg. So the action is given by as follows. Half the sigma down power sigma. Half plus the potential B of sigma. So this is it's Lambda theory. So Lambda theory means that sigma is a free scalar field. This is a scalar field. And the potential is given by as follows. So this B of sigma is potential. And that will be given by G1. Okay, so this is polynomial potential. So polynomial potential. So these are coupling constants. These are coupling constant. These are coupling constant. And then, so here you may wonder. So this is 2p minus 4. 2p minus 4. But you may wonder. So this is the sorry, G. 1, 2, 2p minus 4, and then why not the sigma 2p minus 3 term? G2p minus 3 term, and this is 2p minus 2, right? So you can scale the sigma, it's a sigma plus some constant, appropriate constant. So one can get rid of this term, one can get rid of this term. Okay, that's easy, you can easily see it. So you can get rid of this term. So that I just get rid of this pressure. And if you consider this theory, this theory is not a free theory. So because of the free means there is no interaction. Okay, interaction. But here you have a potential, the interaction term. And then if you consider this is a classic action, and you can consider quantum field theory with this action. Essentially, you just consider the path integral of this one. And then, so the Zamolodchikov proposed, again, proposed that this will flow. Now, G theory flows to minimum model. Unitary. So MP, or this one is the MP and P. So P is exactly the one appearing in this potential. Okay. So minimum model is constructed by using representation theory of universal algebra. So what we did is that so let's recall. What was that? So there's a primary field like this way, and then we look at like this way. And you just forget about this edge primary and look at the inside primary, and then cross under OP and so on. So this is completely constructed. This CFT is constructed from pure representation theory of universal algebra. There's no Lagrangian. There's no information about how the field interact with each other and so on. We just have a universal algebra representation, and we just construct the primary field out of this representation of the universal algebra. That's what we did. So this one, there's no action and nothing. It's just a CFT. If there's a 2D CFT, you have a universal algebra, and we construct some minimum model which has finite many primary field, and then they are closed under OP. That's CFT. This CFT can be realized as the fixed point of this Lagrange theory with this very simple action. So with one scalar field with this potential. That's the proposal of Zamolodchikov. And that's we are going to see from the next lecture. I don't think I have a time to talk about this one. And then, yeah. So that's what we are going to see next lecture. And yeah. I think it's a good place to stop, even though it's still 10 minutes. Let's stop here and leave for question. Any question at this moment? Or any comments and suggestions about this course? What you want to learn or what you want to learn in coming course. So my plan is to talk about this RG float next time. After that, we are going to move the higher dimensional conformal field theory. That was my plan. That's my plan. But do you have any request? Do you want to continue to learn 2D theory? That's also fine. That's also fine. I mean, if you have any comments or suggestion, please send whatever, WeChat message, email, whatever is okay. My plan is to next time, so I will talk about this flow to the minimum model from Lambda model. Then after that, we move to the general CFT in general dimension. So that is the plan. Do you have any comments, suggestion, request?
I have a question about the c-theorem.
Okay.
So we have a basic assumption that the function, the combination of the energy will be answer. But in general relativity, the partial derivative is replaced by the covariant field. So can this c-theorem apply to general relativity?
Question. Most likely, yes. So this c-theorem is the yeah, I think so. I think so. I don't see any. I mean, if you use the if you use this one, I think it's not so difficult to generate stuff. Two-dimensional version, it's not so difficult because I mean, it's in two-dimensional manifold is Riemann surface, and the Riemann surface is everything can be written locally in holomorphic and anti-holomorphic derivative. So in two-dimensional, this is the covariant derivative, but you can just make it some more like a partial derivative with up to some small function. You can just make it this small function by using some complex analysis technique. So it's not so difficult to make the generate the c-theorem to the curved background space-time version of the c-theorem. I think it's a good project for some research as for student, I guess. I think maybe, yeah. But yeah. But one thing you have to be careful is that if you put that theory on the curved background is the really this is no longer 0, c over 12 plus minus of r. So even conformal field theory on even CFT fixed point, the trace part of stress energy tensor is no longer 0. So they're proportional to the curvature of this background matter. So you have to be careful about this point. But apart from that, I think nothing prevents you to generalize the c-theorem in the curved background. Any other question? Okay. If not, I mean, my plan is to talk about this one next time, maybe 1.5 hours or 2 hours. After that, I'll move on to the something different than the or maybe I will go to the last section of this entangled entropy of 2D theory. That may be good for some students. That's also one option. So all lecture of the last section have an entangled entropy section, and the c-theorem are also involved. Maybe that one is also maybe interesting to learn. And after that, maybe we can move on to the higher dimensional conformal. I'll think about it. I mean, if you have any requests, just tell me. In person, WeChat, email, whatever is okay. Just send me a message. Okay, let's finish.